Hey guys, here's a freestyle for you. Given f of x equals 4, find f prime of x. We just want to remember a little bit about an equation that looks like that. That's going to be what? A line that crosses the y-axis at 4. And that line, it's best to call that horizontal, right? This is y equals 4, meaning that it has ooh, that 4 looks terrible. Meaning that it has a slope of what? What is the slope of this line? Well, I'm hoping you remember that the slope of that is 0. There's a good reason for it. If I take a point right here and I take a point right here and they both have a y value of 4, let's say for example -2, 4, and let's say for example this is -1, 4, then when I try to calculate a slope, I'll do 4 over 4, 4 minus 4 over -1 minus -2, and it doesn't matter what I get on the bottom because, ready, if I divide 0 by anything, I just get 0. So that's going to be my slope when I take the derivative as well, only I wanted to show you with the calculus notation. So right now we know then, ready, that the derivative is going to be 0, and that's because we remember that this is the same thing as the slope of that line, and that horizontal lines have a slope of m equals 0. Okay, so now then, how do you actually do that work? Well, I mean, if you conceptually, I did it on the left. Here, let's say I'm going to do it algebraically using the power of limits. And I'm going to do that by saying, hey, if I want to know what x is, I pick an input value. I, in this case, already know what the output value is always. It's 4. And so even if I try to pick a moment in time where I'm just slightly farther away from x, remember that's the concept that we're dealing with here with these limits, that I say that I want to have my x value and then I want to go a very small distance away from that, and that's what I'm calling h. And then I'm going to use this algebraic trick eventually to make h disappear. It doesn't matter where I was on the x-axis, I will still end up with a 4. And notice there's no h, there's no x, it's just 4 because y is constantly, the output is constantly going to be that 4. So my limit then is the same thing as my derivative, f prime, well, I'm going to write this a little bit neater, f prime of I'm going to write this neater, f prime of x equals the limit as h approaches 0, ready, of something minus something over something minus something, and this time I'm actually going to do something minus something. You've noticed in class that I get kind of bored of saying x plus h minus x, and that these things cancel out because x minus x is just 0, and that's how come I'm left with a limit that just has, ready, an h on the bottom. But in this case, I thought it was worthy of going over because on the top is so weird that you get a little freaked out. Remember, this is my second y value, this is my first y value, and I take a 4 minus a 4, and what do I end up with? I end up with a 0. And so a lot of kids would be like, well, we still have division by 0 here. And I have to tell you that the answer to that is no, and there's a reason why, which is that at the moment that I am realizing that I'm trying to divide 0 by anything, I should automatically move on to the moment where I'm saying, nope, that's just 0, right? 0 divided by anything is 0. So really, my derivative is going to be the limit as h approaches 0 of 0, which is just 0. There's no h to plug in anymore. Okay, and that's how come I end up with 0. So this is a really powerful thing for us because it turns out that anytime I want to take the derivative of a constant, I will always get 0. So this is supposed to be number 2 here, and it says given that f of x equals c, where c is any real constant, find the derivative. Ready? F prime of any constant will, if f is any constant, will give me 0. And here's the really quickly I could do this, right? X f of x, I have that I'm plugging in x, I get a constant. I have that x plus h, I get a constant. My derivative f prime of x is equal to the limit as h approaches 0 of a constant minus a constant all over h. That ends up being the limit as h approaches 0 of 0 over h, which gives me, ready, the limit as h approaches 0 of 0, which is 0, and that is my derivative. So now we move on then. What about if it starts to look a little bit more complicated? I've got f of x now equals 6x minus 1. And I'm thinking about that guy, and I'm saying, well, that's still a line, right? But it does have a slope. This line, it goes up 6 and over 1, up 6 and over 1. So that slope right here, I wonder if that will be my derivative, question mark. So let's try it, okay? So I'm going to say then that I have, ready, x and f of x, and I'm going to say then that when I plug in x, I get 6x minus 1, and that when I plug in x plus h, what do I really get? I get 6 times x plus h minus 1. And this is really going to be what? 6x plus 6h and minus a 1. And so I want to do my limit. I want to say that the derivative is going to be the limit as h approaches 0 of something minus something, and the somethings are 6x plus 6h minus 1 and a 6x minus 1. And these are all over, ready, h. And the 6x minus the 6x disappears. Sorry, that's supposed to be an h. And the minus 1 and a plus 1, remember there's a negative here and a negative here, so that turns into a plus 1. That disappears as well. And I know it's kind of messy, so let me rewrite it. The limit as h approaches 0 of 6h all over h is something that I can totally find because, ready, the limit of a number, if it's just a plain old number, is going to be, ready, 6. Ta-da! So hopefully we're ready now to do f of x equals mx plus b, which is just the generic form of a linear equation where m is your slope and b is your y-intercept. And I'll mention that b is just a constant, and so I'm expecting it to drop out because the derivative of a constant is 0. So let's see if that actually happens. We have x and we have f of x, and so if I plug in any old input, I should take that input, multiply it by m, and then add b to it. And if I had any old input and plus some tiny incremental amount, then I would say that I'm going to take m, I'm going to multiply it by that input and that tiny incremental amount, and then I will add b to it. And so when I'm trying to find the derivative of f of x, what I will end up getting is something minus something, the limit as h approaches 0 of something minus something all over h. And the somethings, ready, are mx plus mh, because I'm distributing here, plus a b. So mx plus mh plus a b. And then I'm going to be taking away an mx and a b because I distribute that negative. So this will disappear, this will disappear, this will disappear, and that'll disappear. And all that's left then is going to be my limit as h approaches 0. mh is on top and h is on bottom. Those cancel out. This is just the limit as h approaches 0 of m, which is totally unaffected by me making h be 0. Therefore, my answer is just m. So yes, the derivative of a linear equation is going to just be the slope when you come back to class, okay? So then I wanted to mention that in class, I did go over this example, and it felt like it was a long time ago, so if you don't remember, here you go, where I went over what happens with an x squared. Okay, there's no constant in front, there's no linear term, there's no constant at the end. So what happens with x squared? If I want to take the derivative of that, well, remember that I have my x and then I'll get my x squared, and I have my x plus h, and that amount is supposed to be squared, which we then expand in the following way. And it's interesting to me that when we expand it, what do I see? I see a 2 right here. And that 2 is times x and times nh. And so what I noticed when we actually went ahead and we put something minus something, that the x terms canceled out, and what we were left with right here got factored, and right there I factored out that h, and all that I was left with right there is that magical 2x. And so some h's canceled out. I had this thing left over, h plus 2x, and that h was the same thing as a 0. And so the 2x was all that remains. And so now I know without a doubt that the derivative of x squared is going to be f prime of x is equal to 2x. So what I wanted to say was the power rule, interestingly enough, it has like only one piece to it. And the power rule, I'm going to come over here to the side. I'm going to tell you the power rule. The power rule says that if you take the derivative of x to any power, then what you are supposed to do is drop that power in front of that x and then reduce that power by 1. So let's try that, okay, on the ones that we've done so far. Ready? The power rule says that if I want to ask you to take a derivative, and don't forget, by the way, this notation means please take the derivative. Take the derivative of x to some power. Okay, so if I said that x was squared, then I would say that n equals 2. And I would say that if you have n and you're supposed to, ready, take away 1 from it, well, if x was 2, if n was 2, then n minus 1 will be 1, right? 2 minus 1 ends up being 1. So I'm going to fill this in and say that I have 2x, and remember 2 minus 1, that gives me, ready, just a hidden invisible 1, which I am too lazy to write down most of the time, and ta-da, I get an x. The only thing about the power rule is that I like to talk about it with another constant in front of it, because kids will ask me, well, what do you do if there's some kind of constant here? Ready? You just multiply by that constant in front. It's a multiplier. That's what it does. That's what the rules, the properties of limits tell you to do with any multiplier. So there you go. If, say, for example, then I had maybe an 8 here, then I would have an 8 here, and my answer would be, ready, 2 times 8 here, and my answer would be 16x, because I just multiply by that number. So that's the power rule. How does the power rule work with a linear equation then? Because I had an exponent, you could see the exponent, and having an exponent of 2 and taking away 1, that made sense. You understand now why there's just a 16x here. But what if I had a linear equation and I wanted to do that? Well, dx, please take the derivative of, how about, I'll make it like negative 0.5 times x. Okay, terrifying. No, listen, again, this is just a multiplier, and so it will still be there when I'm done. Also, if it's a linear term, then here, let's do this in green. If it's a linear term, n will equal 1. And if I take away 1 from n, I will get 0, right? Because 1 minus 1 is 0. So ready? There is a hidden invisible x to the 0 right there. What? Yeah, x to the 0. You remember your rules for exponents? Anything to the 0 power is just that same thing. So if I had, remember this could be written like this, negative 1/2 x, and I take the derivative of that, well then I get a negative 1/2 as an answer, as a final answer. Or if you're really loving the fractions, you could say negative 1/2. So what then about finding more complicated derivatives? Well, 6x squared, the derivative, ready, f prime of x should be 6 times that 2x, and then the derivative of 5x is 5, and the derivative of negative 1 is 0, and so my answer will be 12x plus 5. Ta-da. So let me just mention then that f of x is really a different function, right? We've factored it and it looks great, but it's too compact for us to be able to take a derivative. So I actually want to say 2x plus 9 and a 2x plus 9 can be expanded. When I expand those things, what do I get? I get a 4x squared. I get 2x times 9 is 18x, and 2x times 9 is also 18x, and 9 times 9 is 81. And so f of x is really equal to 4x squared. These guys can be collected, and 18 plus 18 is 36. So I get a 36x, and I have plus an 81, and then here I had minus a 5. And so altogether then f of x is really this. It's 4x squared plus 36x. 81 minus 5 is 76. Okay? And if I want to find the derivative f prime of x, I will end up with 4x plus 36 plus 0. For a while, just to help you guys when I'm doing this, you might like this, that I'm going to remind you the derivative of a constant is 0, and I'm going to write it down for you just for a while, just so you don't forget. But the final answer, I just put a box around it because I've already done enough. You know what I mean? There you go. F prime of x is 4x plus 36. And I leave it to you to try it in the old-fashioned way, and you will see, old-fashioned meaning the limit definition of a derivative, you will see that it works out to be that way literally every single time. Okay, one last one then, finding the derivative of x cubed. Now we did one of these in class, and the notes on it, I'm not sure that everybody got to take those, but I will mention the one that we did in class was x cubed plus 1. And I'm hoping now that you recognize that that plus 1, it's just a constant. It's going to disappear. So what I'm trying to do is I'm going to go over x and f of x, given if f of x is x cubed, then I have x, and this is going to be x cubed, and this is x plus h. And by the way, I'm going to use Pascal's triangle in these notes to expand this, that I have x cubed, and I have h squared, and I have an h and an x squared, and then I have an x being cubed. And with the Pascal's triangle, I'm going to say a 1 here, a 1 here, a 3 here, and a 3 here. And I'm going to move on. And if you want to use Pascal's triangle, great. Or if you want to do a series of boxes to help you work this out, that is also great. Okay, so here we go then. What about the derivative? All right, well, let's say that f prime of x is going to equal the limit as h approaches 0 of something, and it's a really long something, minus something that's a really short something, and all of that is over h. So I want to say that I have x cubed. Remember, I don't need this 1 right here, and I don't need that one right there either. Oh, sorry, that's supposed to be an h cubed. Was that bothering you? I apologize. Okay, I fixed it. X cubed plus 3h squared x plus 3hx squared. I knew I wasn't giving myself enough room here. Plus h cubed, and that minus is an x cubed, which is a bummer because the only things that cancel out are those, and I was kind of hoping for more, right? But remember, on factoring this, I did teach you guys this tool a long time ago, and it's very rare that we ever even have a chance to use it. But if I say I have a 3h squared x, and I have a 3hx squared, and I have an h cubed, the only thing that I can factor out is just one single h. Here I will have left a 3hx, here I will have left a 3x squared, and here I will have an h squared. And so that's the best I could do for factoring that. So I say then that this is really equal to the derivative. I kind of wrote over there, so I'm gonna move over. Sorry, the derivative of my function is equal to the limit as h approaches 0 of, ready, h times 3hx plus 3x squared plus h being squared and all over h. And these h's disappear. And that's awesome. And now I don't have a denominator anymore, so I'm not worried about division by 0. And I'm going to go ahead and plug in that h is 0. So ready? So I have 3 times 0 times x plus 3x being squared. And I have a 0 being squared. Well, this is 0, that is 0. So my derivative, f prime of x, is equal to 3x squared, which is exactly what the power rule said it should be. So I've done it this way. What if I use, ready, the power rule? Power rule for please take a derivative of x cubed. Ready? It says that if your exponent was 1, that you should drop that exponent into the front and make it a multiplier. And you should also figure out what happens if you take away 1 from that exponent. Well, the exponent was 3, so let's take away 1, and we should get a 2. And that is the new exponent. Ta-da! There you go. Your answer is 3x squared.